Hello, guys. So, welcome now to part three. So, now in the last part, we spoke about glycolysis and where we broke down glucose to give us two pyruvates, but it also gave us two net ATP. In total, it was four, but because we sacrificed two at the beginning, we get two as net, and we also got two NADHs. Well, this is great because we now we've got an ATP, and we can actually use this to fuel endogonic reactions in the cell. But what happens to the NADH? What's the fate of it? Because NADH needs to be recycled back to NAD plus. Because as we said in part one, we need NAD plus in big excess because they need to accept these electrons being released. They need to. Because having, first of all, you want to take those electrons because they have energy, but having electrons moving around in your body is very dangerous as well. That's something I forgot to say. So you need these NAD pluses. So we need to basically recycle NADH that we created back. So the fate here is governed by whether we have oxygen or not. If we have oxygen, which is aerobic respiration, NADH is going to keep passing the electrons until they reach oxygen. And this actually produces a significant amount of ATP, which we will learn later. If oxygen is not available, basically NADH will then pass the electrons to these organic molecules as the final electron acceptor. Here, you don't create actually ATP by doing this, but at least you've recycled NADH back to NAD plus. And this only happens when oxygen is not available. So this is basically what happens. So let's imagine you have pyruvates here, and you have the NADHs. If there's oxygen, then basically pyruvate, so the pyruvates that we created, will be oxidized into acetyl-CoA and will go into the citric acid cycle, which will go again into the electron transport system, which will help the NADH give the electrons to water. If there's oxygen, then it will go into this full complete circle. This is the aerobic respiration. If not, then pyruvate that's been produced will then actually be turned into lactate. This is mostly in humans in the muscle. And so basically this will be done, hence this will be pyruvate will be reduced to lactate. And this reduction will help NADH actually be recycled back to NAD plus. In plants, or in sorry, not plants, in bacteria like in other eukaryotes like yeast, pyruvate is reduced into acetaldehyde, which is then further reduced into ethanol. And this further helps NAD become oxidized back to NAD plus. And this is actually how you create alcohol. I do beer actually at home. I'm a home brewer of beer, and this is actually what I do constantly. I create a lot of sugars, specifically pyruvate sugars, and what I do is actually I close off the oxygen and I add yeast. Because yeast, what they're going to do is they're going to convert these sugars in pyruvate into acetaldehyde and ethanol, and which then gives me, my beer at the end by actually cutting off the oxygen. So we're gonna focus a lot on the aerobic in a case where we actually have oxygen. So then, as we said, it starts off by actually then oxidizing pyruvate. So the first step is then oxidizing pyruvate, and this happens then in the mitochondria. So if we go back here, glucose now is broken down, and then you have basically pyruvate. Pyruvate is then taken into the mitochondria, and this specifically happens in the inner mitochondrial membrane because that's where the enzyme is. And there basically it's going to oxidize pyruvate into acetyl-CoA. So again, this I'm going to show you here. So you get pyruvate, and with the help of an NAD and basically the CoA, this coenzyme, you're going to get acetyl-CoA, coenzyme A, plus an NADH, CO2, and H plus. So this is what happens when you do this oxidation of pyruvate. It's a three chemical process. It actually happens in three steps. That's why this pyruvate dehydrogenase. So this is the enzyme actually has three enzymes. It's a multi-complex enzyme which has three and actually converts pyruvate into acetyl-CoA, and also then gives you NADH, CO2, and a hydrogen plus. So this you need to memorize. So as we said, this happens in the inner membrane of the mitochondria, and where pyruvate is oxidized into acetyl-CoA. Because then acetyl-CoA is the first step to start the citric acid cycle, which we're going to talk a lot into details. So the citric acid cycles, the main purpose of this is to further oxidize pyrite much more. And what you're doing here is you're creating ATP, but you're also creating a lot of much more NADHs. So you're further building on glycolysis by creating more ATP, but a lot of these NADHs. Because we're gonna use all these NADHs that we created to push the electron transport system at the end. So keep that in mind. So the Krebs cycle is 9 steps, which you also have to memorize, and you could basically divide them into 3 segments. The first one is when you actually get this acetyl CoA, and you basically combine it with oxaloacetate to create citrate. Acetyl CoA is a 2 carbon um, molecule. Oxaloacetate is a 4 carbon. So citrate becomes 6 carbons. Then this 6 carbon is rearranged, so you isomerize it, and then you basically decarboxylate it. So you start removing carbon dioxide a lot from it, and this actually helps you a lot in giving a bit of energy to fuel ATP. And then you regenerate oxalate. So then it's because you need always oxalate to push this forward. Hence, this is why it's called a cycle, because it goes in circles. Because basically, the final product that you're trying to basically will be the beginning. So here, the final product will go back to the beginning. So also here, when you decarboxylate, you're actually losing a lot of electrons, and this is where you actually get NADHs. So we're gonna go into a lot of details about this. So this is just the overview, but I want to go straight into this, into how this is happening. So here, as we said, you have acetyl CoA. So we basically got pyruvate. We actually oxidized it into acetyl CoA. So acetyl CoA comes in, and all of this is actually happening in the matrix of the mitochondria. So again, please always know where this is happening. So this is happening inside here, the mitochondria. Okay, so let's start. So you have acetyl CoA, and as we said, it combines together with this oxaloacetate, so which is 4 carbons. And basically, what you get with this enzyme called citrate synthase, you get citrate. So CoA actually is removed, and you get this molecule called citrate, which is 6 carbon. Then you isomerize it using alkoxygenase to create isocitrate. Once that this is isomerized, so this is two reactions to fully isomerize it from citrate to isocitrate. Then isocitrate is first oxidized. And by first oxidized, basically here we're actually decarboxylizing, we're removing CO2s. So we're basically removing electrons, we're breaking them, and the electrons that are being removed are being given to NAD plus to give you NADH. So that's the first oxidation. And then this gives you basically alpha ketoglutarate, which is a 5 carbon, because now we removed 1 carbon out, so we have now 5 carbons. And this goes for a second round of oxidation. And this happens with alpha ketoglutarate dehydrogenase. And basically, again, very similar to what's happening here. You basically CO2 is removed, electrons are removed as well, and they're going to be given to NAD plus to give NADH. So this is our second NADH molecule being created. So this gives you basically this gives you the second oxidation, but we also add a CoA enzyme back here. So the one we lost here, we put it back in here, and this will give you in final product a succinyl CoA. So what we've done here with the help of alpha ketoglutarate dehydrogenase is that we removed carbon dioxide, we substituted with actually a CoA, so CoA enzyme group, and basically we've given electrons to NAD plus to reduce it into NADH. So now we have succinyl CoA. Succinyl CoA is then basically going to be completely then broken in this CoA. When you break this actually sulfide bridge over here and remove this basically this is an CoA, when you remove the CoA, so basically this here we break it down, you're providing a lot of energy. So when you provide that energy, you're gonna fuel GDP, which is similar to ATP, but is using a different nucleotide, which is guanine. So you're fueling guanine diphosphate to become guanine triphosphate, and this is then gonna transfer a phosphate here to adenodiphosphate to ATP. So this is the first ATP that we created. So this is all done by succinyl-CoA synthase. So it's literally breaking down this group over here, and that's releasing a lot of energy that's fueling this GDP to GTP, and this GTP is then transferring the phosphate into ATP to ATP, and then you get actually succinate. Succinate is going to get to its third oxidation using succinate dehydrogenase. So we're actually going to reduce it. We're going to break some bonds, specifically this one here, and we're going to remove these basically this double bond and electrons, and we're going to pass this into FAD. So we spoke about FAD. FAD is very similar to actually NAD. It's just a different nucleotide. That's basically the F. And this gives you a reduced version, this FADH2, which is accepting now electrons. So this is the third oxidation. And this gives you fumarate. Fumarate is then going to be actually then regenerated into oxoacetate, and going to go to a basically a fourth oxidation later on. But basically, we're going to do is add a water using fumarase, and that's actually going to give you this malate. And then malate is going to be then dehydrogenated, meaning that you're going to remove hydrogen, specifically as you can see here, and that's going to basically oxidize it, and then basically give the electrons to NADH to fully get NADH. So this is the cycle. So you've created one, two, three NADHs, an FADH2 molecule, and an ATP. And this is basically, this is from one acetyl-CoA coming from one pyruvate. So imagine from two pyruvates, you're going to get double of this. So you always remember that. So each acetyl-CoA entering the citric acid cycle gives you two molecules of CO2, three NADHs, one FAD, one ATP, and regenerates oxoacetate. So that's the yield of the citric acid cycle. So when we break down glucose using glycolysis and citric acid cycle, you have this is the final that you get: six CO2s, four ATPs, 10 NADHs, and two FADH2s. So ATP is great. We have this amount, but what do we do with these guys? These guys have a lot of electrons now. They've gathered a lot of electrons. We need to use them. Basically, we need to use these energy that they have. And this is where it's going to push us into the final uh, biochemical reaction, which is the electron transport chain, which I'll be speaking in basically in the next part.